Hello students, welcome back. Let us now go back to section 3 of this notebook, the change of basis theorem, and let's talk about the technical detail. It goes like this. Given vector v, it can be written as a coordinate expression x1, x2, x3 all the way up to xn based upon one basis system, and y1, y2, y3, y4 all the way over to yn based upon different basis system. You see, coordinate expressions are unique, yes, but unique when the vector is given and the basis is given. Here we have same vector but two different bases, so that's why we're having two different coordinates. So this expression, first coordinate expression based upon one basis system, and the second coordinate expression based upon another basis system actually mean the same thing. And here's a visualization. We are looking at same vector, this point, or more precisely speaking, vector from the origin to this point. It's 4, 3, or 4v1 plus 3v2 with respect to this blue system. v1 is horizontal, v2 is vertical, both have the same size. This is standard system, standard basis. Now if you have some tilted basis, the same point, same vector can be written a little bit differently. Instead of going to 1, 2, 3, 4 units horizontally and 1, 2, 3 units up, we are moving 1, 2, 3, 4, a little bit less than 5 units in W1 direction, and 1, 2, 3, and about 3.5 in the second direction. And we have two different coordinates, 4, 3 versus this that, which is approximately that. So you see, same vector can have two different coordinate expressions, and that's because we have two different bases. Now, how are those bases related to each other? Well, here is the relation. It is possible to express one basis system with respect to another because, after all, W1 is a vector in V, and then V1 through Vn is a basis, so it generates entire V. So any vector can be written as a linear combination. In particular, W1 can be written as a linear combination of V1 through Vn, and that's this first row. I'm using the color coding to help you understand this better. W2 can be written as a linear combination, and that's the second row, and so on and so forth. The last element, Wn, can be written as a linear combination, and that's green. Okay? All right. Now, how are those coordinates x1 through xn and y1 through yn related? Here's the conclusion. X equals to ty, where this matrix T is given by the column, blue column, given by the blue row, and then the second column given by the second row, and so on and so forth. And the nth column is associated to nth row from here. So W1, W2, W3, all these are written as column, column, dot, 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 column. All right? Then we get the matrix T, and this matrix T is called a transition matrix. And based upon the transition matrix, we have X equals to Ty. Now, as for having those column, column, and column, haven't you seen this before? You must have seen it before. Let's go to the previous module, module 7, and let's go to matrix associated with a linear map. Wait a minute, I don't have to do this. I can go over to review here. That's more effective here. Matrix associated to linear map. Yeah, okay, all right. V and W be vector spaces with faces V1 through Vn and W1 through Wm. And if you select W is equal to V, then we're gonna get W1 to Wn, and that's about it, as a matter of fact. And then the linear map W equals to L of V can be written as matrix multiplication Y equals to AX, where the matrix is given by the coordinate expression of each basis vector, or the images of each basis vectors as columns, columns, and columns. Do you remember this? I'm not asking you to reproduce the proof. I'm asking you to remember this matrix expression given by column, columns, and so on. Do you remember this? Exactly the same thing is taking place here. For basis W, we have column. Basis W, we have column. And repeat, repeat, repeat. Last basis W, we have column. Hey, it's the same setting as before. So the matrix related to the linear map versus the transition matrix, essentially they are the same. But in the end, there's a bit of a difference here. Instead of y equals to ax, we have x equals to ty. So there's a bit of a difference here. And even that can be mended in a little higher level, but I don't want to go there. In any case, remember this. Columns for the first basis, column for the second basis, third, fourth, fifth, and so on. Column for the last basis, and you can get a transition matrix, and that the formula is x equal to ty. Now, do we have enough time to prove it? Okay, let's prove it. Under the basis W1, W2, all the way up to Wn, we can express arbitrary vector v as follows. y1, W1 plus y2, W2, all the way up to yn, Wn. You see these are the coordinates. Okay, and then I'm using color coding here to understand. I'm using color coding here to help you understand this thing. And then what is the relationship between v and w? Here we go. Each w can be written as a linear combination of v's. And this row goes into here. The second row goes to the second, and so on and so forth. The nth row goes to the nth, and then do your computation, and this is what you get. Each parenthesis here is the substitution. Now, let's break up these parentheses and rearrange. So multiply y1 times tau1, 1, y2 times tau2, 1, all the way over to yn times this, and that's going to give me coefficient of v1 over here. And now y1 times this tau1, 2, y2 times tau2, 2, yn times tau n2 these, that'll be the coefficient for the second vector v2, and repeat all these. That's how we're going to get this line. And then we compare that with coordinate expressions of the same vector v with respect to the basis v1, v2, all the way over to vn. What do we have? This is x1, that's x2, and then x3, x4, x5, and so on, and that's xn, and that's the conclusion here. x1 is that, x2 is that, and so on, yn is that. And it looks really confusing here, but the color coding really helps. This can be decomposed into this matrix expression, where first column, they're all multiplied into this first entry there. That's red, red, and so on. That's green. Those are green. Do you see all these? If you do matrix multiplication, row times column, that's basically this. Blue, blue, red, red, and then next color, always green, green. Second row, third row, all the way to nth row. Do you see this? And that is the conclusion. That is precisely what we wanted to prove all along. So what do you have? We have this column, and so on, all these columns. That's a transition matrix. And then we have x equals to ty. Let's have a application of this, and that application I think will solidify the understanding, because if you look at it like this, oh my, there are too many indices even in this state is confusing. Okay, here we go. Here's a change of basis. Same vector v can be written as 4e1 plus 3e2, where e1 and e2 are standard basis, horizontal and vertical, and 3y1 plus 4y2. Okay, all right. And we're talking about this kind of visualization. Yep, same point here and there by selecting W1 and W2 cleverly, and then we have another lattice point like that. Okay. In the previous example, the second expression was not lattice point, integer comma integer, so it was a little bit harder to calculate. Theoretically the same. I'm having this simpler number here just for the computational purpose. Okay, all right. Now what are W1 and W2 in this case? In this example, we are taking W1, this one is 2 comma negative 1. 2e1 minus 1e2, 2 comma negative 1. W2 is this one, the second vector. I'm running mouse over here. Negative 1 half comma 3 halves. Okay, that's the second vector. So what's the transition matrix? Let's go back to this. You don't really have to follow all these indices with tau 1, 1, tau 1, too complicated. Use color coding. First basis, second basis, third, fourth, fifth. They are going columns and columns and columns, right? Just like all the matrix expressions are. So here in this example, the transition matrix is the column 2 comma negative 1. Let's color code in blue. And negative 1 half and 3 halves. That's a transition matrix. And then what's x? This point. 4 comma 3. All right, 4, 3. What's y? 3 comma 4, as you can see. Okay, 3 comma 4. And do we have that transition formula? X equals a ty. Let's check. Let's check. X, which is 4, 3, is equal to, this is t, and then y. Is this true? Is this true? Well, let's check. Three times 2, that's 6. Negative 1 half times 4, that's minus 2, isn't it? And matrix multiplication, 3 times negative 1 is negative 3. And 4 times 3 halves, that's 6, isn't it? So am I getting 4, 3 as expected? Okay, so everything fits, everything checks out. Now, there's very little chance you're going to see in the exam because this is already optional video on appendix topic. Our textbook author put this one as optional topic as well. So little of no chance you're going to see this in exam, but let's assume that in the near future we have linear algebra 2 and we end up covering this, and then let's suppose we have some exam problem like this. A possible problem is kind of like this. You see, I give you these bases, E1, E2 of course, but W and W2 are like that. And then x4, 3 is given. And then what is this? 3, 4 is the answer, of course, but I withhold this information, this red part, and then I can ask you to find out. And basically it's coming from, that's going to come from this equation. X equals to ty. So I don't know y. So I have to figure these out. And what is this? This is a system of linear equations, and just 2 unknowns and 2 equations, you can easily identify these. So just set up the matrix equation, and then you're going to get a system of linear equations. So if I give you, let's see, 2 bases, one is standard basis and the other is like this, then point 4, 3 can be written as like this. Or maybe I can create something right now. Instead of 4, 3, 5, 2, okay. And then what is that coordinate expression with respect to the second basis system? It's basically this equation. And then you can solve it like this. So 2x minus 1/2 y, and then minus x plus 3/2 y, isn't it? And then therefore we have system of linear equation 2x minus 1/2 y is equal to 5 and minus 1x minus x plus 3/2 y is equal to 2, and you can find what x and y are by solving the system of linear equations. So, you can get these done. So what did we do? We worked out problems related to the transition matrix through change of bases. And the transition matrix we can get by columns. First basis, second basis, third, fourth column, and then the last basis vector. Column, 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 and so on. And the equation is x equal to ty. That is the conclusion. We proved it, and we went through an example problem that utilizes this. How about this one? W1, W2, W3 be a basis given by these, okay. And then find a coordinate expression of 1, 2, -4 with respect to this basis. Okay, that's a nice problem. So transition matrix should be, let's see, insert matrix. We have 3 by 3 matrix, and it should be 2, 1, -1, the column, isn't it? And then -1, 1, 0, the column. And then 3, 1/2, -1, the column. And then x is equal to 1, 2, -4. One, 2, -4. And then y is of course unknown. So x, y, z unknown. And then we have x equals a ty, that is one to 4 equals to t times y. Now, setting up and solving this system of linear equations to find out x, y, and z, that's elementary. Tedious but elementary. So I'll stop here and ask you to figure it out. Let's see, what did I do in the solution here? Okay, all right. Instead of x, y, z, I did y1, y2, y3, okay. And then solving this system of linear equations, sorry about the typo, you're supposed to get this answer. And looks like some ugly computations follows from here. Oh my, I did all those computations. But of course, much better solution is here, using computer algebra system. Yes, okay. So 2x minus y plus 3z equals to 1. 1x plus 1y plus 1/2 z equals to 2. And then negative 1x plus 0y minus c is equal to negative 4. And there goes the system. Yeah, it's not difficult. It's elementary, just tedious. If you do it right, you're gonna get this answer. Okay, I'll stop here.